Why is the rain melting our buildings? I mean, seriously, it sounds like the plot of some dystopian sci-fi movie, right? But it's actually an ongoing reality in cities all across the globe. We literally have invisible gases floating above our heads that are eating away at solid stone. So, how does that even happen? Well, today we're going to find out. Welcome to The Explainer. I'm so thrilled you're joining us. Today, we're stepping into the shoes of lead scientists to decode exactly how these invisible, microscopic chemical reactions create massive, undeniable impacts all over the world. We're going on a journey, starting from the tiniest atoms and scaling all the way up to our global atmosphere to really understand non-metal oxides and the environment. Okay, here is our lab syllabus for today's session. 1. Meet the non-metal oxides. 2. The acid-rain equation. 3. The greenhouse effect explained. 4. The power of methane. And 5. How we fix this. Let's dive right in. Section 1. Meet the non-metal oxides. If you really want to grasp this topic, you absolutely need to lock in this foundational definition. A non-metal oxide is simply an oxide formed from a non-metal and oxygen. It's really that simple. This basic, microscopic combination is exactly where our entire story begins. Now, what's super interesting is how clearly we can categorize the main culprits here. When non-metals violently combine with oxygen, we get some names you've definitely heard before. Take carbon, for example. It forms carbon dioxide, or CO₂, and carbon monoxide, CO. Then you've got sulfur, which gives us sulfur dioxide, SO₂, and sulfur trioxide, SO3. And nitrogen, that forms nitrogen dioxide, NO2. Keep these specific formulas in your head because they are going to cause a whole lot of trouble very shortly. But here's the thing. Not all non-metal oxides behave the exact same way. The vast majority of them are what we call acidic oxides. This means they actually dissolve in water to produce acidic solutions, things like carbonic acid, sulfuric acid, and sulfuric acid. However, there are a couple of very important exceptions. Some non-metal oxides are neutral oxides. They produce neither acids nor alkalis. The two major ones you really need to know are carbon monoxide and nitric oxide. Actually, that is a vital exam tip right there. Always remember those neutral exceptions. Section 2, the acid-rain equation. So, the crucial point here comes down to this number, 5.6. Normal, unpolluted rainwater actually sits at a pH of about 5.6. It's already slightly acidic just because carbon dioxide naturally dissolves into it. But, and this is a massive but, when the pH drops below 5.6, it officially crosses the threshold and becomes acid rain. So how does it drop below 5.6? Well, it's a destructive chain reaction. Step 1 begins when we burn fossil fuels like coal and diesel, which releases sulfur dioxide. That SO2 goes up and dissolves in rainwater to form sulfurous acid. Then, in step 2, further oxidation turns that into highly corrosive sulfuric acid. Step 3, add cars to the mix. The massive engine temperatures force nitrogen and oxygen to react, forming nitrogen dioxide. That meets water up in the sky to form nitric acid. We are quite literally manufacturing acid up in the clouds. And this microscopic chemistry leads to some pretty devastating macroscopic effects. Out in our forests, acid rain damages leaves, reduces photosynthesis, and severely stunts plant growth. In our lakes and rivers, it drops the pH so drastically that it disrupts entire aquatic food chains. And hey, remember our opening question about the melting buildings? Well, here's the answer. Sulfuric acid reacts with limestone, essentially turning solid structure into calcium sulfate, carbon dioxide, and water. The building literally just washes away. Section 3. The greenhouse effect explained. We hear this term thrown around all the time, but let's lock in the exact definition. The greenhouse effect is the warming of the Earth because greenhouse gases absorb and re-radiate infrared radiation. It all starts with the sun's energy reaching Earth. The Earth absorbs this energy and then emits it back out as infrared radiation. Greenhouse gases like carbon dioxide, methane, water vapor, and nitrous oxide absorb some of that infrared radiation and re-radiate it, warming the atmosphere. And here is the absolutely key thing. This is a natural, beautiful, life-saving process. Without it, Earth would be a frozen, uninhabitable rock. And that brilliantly illustrates our tipping point. There is a massive difference between the natural greenhouse effect, which keeps Earth warm enough for life, and the enhanced greenhouse effect. By constantly burning coal, oil, and natural gas, and through mass deforestation, human activities are just pumping excess greenhouse gases into the atmosphere. More gas means more heat becomes trapped, We shift from a natural, cozy blanket that keeps us warm to a heavy, suffocating quilt that's causing global warming. The stakes of this enhanced greenhouse effect are planetary. Increased global temperatures lead directly to rising sea levels and melting glaciers. We're already seeing more extreme weather events, devastating flooding in some areas, and then crippling droughts in others, which leads to severe habitat loss and reduced biodiversity. These aren't just distant, theoretical issues. This shifting climate threatens our cities, our food supply, and our immediate future. Section 4. The power of methane. Now, carbon dioxide gets most of the headlines, sure, but methane? Methane is actually a much stronger greenhouse gas. It possesses this sheer invisible strength when it comes to trapping heat. Even though there's technically less of it in the atmosphere compared to CO₂, you absolutely cannot underestimate its potency as a major threat to our climate. So where exactly is all this highly potent gas coming from? The sources are incredibly diverse, and honestly, some of them might surprise you. A massive amount comes from agriculture, specifically large-scale rice fields, and yes, the digestion and burps of millions of cattle. We also see huge methane emissions off-gassing from decaying organic matter sitting in our landfill sites and leaking from industrial natural gas pipes. So it's coming from our food, our trash, and our fuel. Section 5. How we fix this. I know we've covered a lot of heavy chemistry today, but here's the good news. The exact same science provides our solutions. Remember that terrible acid rain caused by sulfur dioxide? Well, we have this ingenious technological fix for that called flue gas desulfurization. Basically, here's how it works. Power stations introduce limestone, which is calcium carbonate, right into their chimneys. As the toxic sulfur dioxide tries to escape, it reacts with the limestone. The equation is calcium carbonate plus sulfur dioxide forms calcium sulfite and carbon dioxide. This brilliant little chemical trap safely removes the sulfur dioxide right at the source, long before it ever hits the atmosphere to form acid rain. And to tackle global warming, we've got a clear, multi-pronged strategy. It all starts with how we power our lives, transitioning over to renewable energy and maximizing our efficiency. We can actively heal the landscape by planting more trees to naturally pull carbon right out of the air. And we can lower our daily footprint by simply taking public transport. On an industrial level, we can capture methane before it ever escapes landfills and trap power plant emissions using carbon capture and storage. The tools and solutions already exist. We just need to use them. We have scaled all the way up from a single non-metal reacting with oxygen to acid rain melting solid limestone, right up to the global threat of an enhanced greenhouse effect. But, as we've just seen, human ingenuity and scientific understanding offer a very clear way out. So I'll leave you with this. If mastering these chemical reactions is the key to saving our environment, what part of the equation will you change? Thanks for joining me on this explainer, and I will catch you next time.